All right, guys, so we got one more problem to do. I'm going to put it up on the screen. So there you go. Now, this is a big problem. It's got a lot of work to do, but I think it's a good example of a lot of things that we're doing. So we basically, if you go camping, if you take a camping stove, you're going to have a propane tank. And then the propane tank, you can connect it to a stove. And when you ignite it, the stove burns, and all the heat that comes from the combustion of propane, you can use it to cook, like if you're going to boil a pot of water. Okay? So don't make fun of my artistry, but that's what we have. Now, question is, if we're going to boil a pot of water, how much propane is it going to require? Okay, and this is, to me, where chemistry really comes to be important, is when we assess real problems that you might encounter in your normal life. Okay, so how much propane will you need to boil a pot of water? So let's start working through it. First of all, if we're going to boil a pot of water, we know the problem told us we're going to start with the water at 22 degrees Celsius. Now it says heat it up to boiling. So we're going to get it to the point of boiling and stop right there. We're not going to fully boil it away into the gas because, when you're cooking, you normally don't boil your pot of water until the water's all gone. That's just not how we normally do it. So the equation we're going to use, Q equals MC delta T. So my mass of my water, again, it just told us it's 2 liters. That's 2,000 milliliters, which is 2,000 grams. So my mass is going to be 2,000 grams. Specific heat of water is 4.184. And then delta T, we're heating the water up from 22 degrees up to 100. That's a change of 78 degrees. Okay, so just based on that, I should be able to multiply that. And I'm going to figure out this is how much heat we actually need to get from the reaction. So 2,000 times 4.184 times 78 equals, and it's about 652,700 joules. Okay, so it's a big number. Okay, so we're just going to put that number aside for now. We know how much heat we have to make. But then we have to think, okay, where's the heat coming from? Well, there's a chemical reaction occurring where we are burning propane. It's an exothermic reaction. The heat from the reaction is what's going to come into the pot of water and do this job for us, which is heating the water up to boiling. Okay? Now, so we need to write a balanced equation. So it's going to be propane. Again, I would give you propane as C3H8. It's a gas. We add O2, and we make CO2 and water. I'm going to put water in a liquid form, although again that's a questionable choice, just depending on how exactly you're going to work the problem, but we're just going to go with it. So balanced equation is going to be a 4 in front of water, a 3 in front of CO2, and a 5 in front of O2. So that's my balanced equation. I need to know if I'm going to do any work with this reaction, like I need to know how much propane has to burn to give off a certain amount of heat. I need to know what delta H is. Delta H for that reaction. I'm going to have to figure it out, and the problem didn't give it to me. So I need to find a way, how can I get the delta H for this reaction? The easiest way is just do products minus reactants using the heat of formation values. So to do that, let's see, delta H of reaction is going to be CO2. If you look it up in the appendix, it's negative 393.5. So it's going to be negative 393.5. And I got to make 3 moles. So it's going to be 3 times that. Plus liquid water's 285.6 kilojoules per mole. And I got to make 4 of those. So 4 minus the C3H8. Actually, that one I don't know. I had to look it up. I think it was negative 104.6. And I am using 1 mole of that, so I can just leave that as it is. And then O2 is going to be 0. So for the reactant side, that's it. And actually, the water, I left the negative, it should be negative 285.6 right there. Okay? So if we do all that, I believe the delta H that we should get is around negative 2220 kilojoules. Okay? Now, what can I do with that? Well, I know how much heat I need to make, 602,000.7 602,700 joules, which is 602.7 kilojoules. So I'm going to go ahead and write that, 602.7 kilojoules. That's how much heat we decided earlier that we need this much heat to get our water up to boiling. And we know that if we burn 1 mole of propane, it's going to produce this amount of heat. So this is the kilojoules per mole. So now I need to bring this information together in the middle and say, okay, well, I need 602.7 kilojoules. And then I'm going to use the delta H as a conversion. It's 2220 per mole. Now, I'm going to put the 2220 in the bottom because I want kilojoules to cancel. 2220 kilojoules per 1 mole of C3H8. Now, some of you might say, well, what about the negative? The negative just tells me that this is an exothermic process. This is the amount of heat that's going to be released when 1 mole burns. Okay? So I can leave the negative off if I'm just like saying this is how much I need, this is how much being released. My moles have my answer of the amount of propane. It's got to be a positive number at the end. It wouldn't make any sense to have a negative value for the moles. So I have to kind of, in the end, just make everything positive for this problem to make sense. Okay? But I should be able, kilojoules should cancel. So if I do 602.7 divided by 2220, that's going to give me the moles of propane. But then when we ask how much of something are we going to use, typically in lab we measure grams. So we would probably want to change this to grams. So I'm going to go ahead and do 1 mole. And then the molecular weight of C3H8 is 12 times 3 is 36 plus 8 is 44. So I'm going to use 44 grams. And when I get that answer, that will be my final answer for this problem. 602.7 divided by 2220 times 44. So my answer is 11.9 grams of propane is the amount of propane that would have to be burned to accomplish the job that I want to do, which is heating up a pot of water. Okay, that's it. That's a big problem. It does bring together the calorimetry, the heat of formation, find the delta H of reaction, and then to get from the amount of heat that I need to the amount of the grams of the reactant that have to be reacted. Okay, so that's kind of 3 different types of problems all in one for this problem. I like it a lot, so make sure you can do it for the test.